All right, welcome back to DellyMaths concept. What we're looking at today is we're looking at calculus. It says can change occur at an instant? So the first question here, it says the number of people who have left an amusement park is modeled by the function L, where L of t gives the number of people in thousands. So this is in thousands, as you could see, who have left the park at t, and T gives the number of hours since 10 a.m. All right. Now, for T is greater than or equal to 0, less than or equal to 6, the graph of the function L is shown on. Draw a tangent line at T equal 1. So we're going to draw a tangent line at T equal 1. What my tangent line. So here's my red line here. That's my tangent line here. This is the tangent that we're referring to at T is equal to 1. Right, so that's a tangent line. We wanted it just to touch that curve, right? So that's a tangent line to it right there. Now, the second question says, give a rough estimate of the instantaneous rate. So this word at that instant. So at T is equal to 1, we're going to look to see what is that. So on our graph with T is equal to 1, if I use the blue line here, go across, basically this is about 400, or you'll see about 4, which would represent 400. Because I put 2,000 here, which is for 2, and a half of that here would have been 1,000. And this is just below a half. So roughly, I'm thinking that this is about 400. All right. So definitely that response here, we're looking at about 400 people. So it's approximately 400 people, right, per hour. At that instance, about 400 people per hour. The next question says here, we're at C, it says, give an example of how to calculate a rate of change that would give a close estimate to the instantaneous rate of change. All right, so we want to give an example of how we can calculate a very close estimate to the instantaneous rate of change at T is equal to 4. So if we're going to give a close estimate, what we're going to do is to pick a number like very close, right, to the 4. For example, we're going to evaluate L of 4, all right, minus, because it's going to be a rate of change, but it's going to be at that instant. So we're going to evaluate L of like 3.9999. We're saying like very close. So we're evaluating these values here. Well, 4 minus 3.9999. So we're actually looking at that. So that will give us a very close, estimate. It's not it, but it's going to give us a close estimate. We're close to the truth at that instance, because you can see there is hardly a difference between 3.999 and 4. So that's going to actually take us to that instance. So that is what we're actually looking for here. Let's take a look at question 2, right? So what question 2 is dealing with? Question 2 says here that the population of a community of wild boars, so we're dealing with wild boars in this case, is modeled by the function B, where B of t gives the number of boar and t gives the number of years since 1990. So this is since 1990. Now, for t is greater than or equal to 0, but less than or equal to 30. All right, so the graph of the function b is shown on the right. So we're looking at our graph right here. Now, let's do the first one. It says draw a tangent at t equal 25. Where t is equal to 25 right there. So we're looking at where t is equal to 25. That's my tangent line, right? Let's go back to the question. So based on what I saw here, so my tangent line was somewhere here, going that way, right? That's my tangent line here. So at t is equal to 25, it says give a rough estimate now. So we did the tangent line. So now we want to give a rough estimate of the instantaneous rate of change at t is equal to 25. what I'm looking at here, as you can see, we have 25 here. So if we take a look at this line here, it does go across at 200 here. But when we look, it happens over like approximately 10 years. So we're looking at 200 over a 10-year period. So basically then what we want to do is we want to work this out because it's going to be 200 over a 10-year period. We're actually getting about 20 boards per year, right? 20 per year. Example, should say, of how to calculate the rate of change that would give a close estimate to the instantaneous rate of change at t is equal to 5. If I'm going to try to find an idea at t is equal to 5, I'm going to do, we have to do this. We're going to have to do b of 5. We have to do b of 5 minus b of 4.999. Like we're going very close to it. So there's a small change right there such that we would just classify it as an instant, right? And we're going to take 5 minus, we're going to have 5 minus 4.9999. So we're suggesting that at that instant, at t is equal to 5, these two numbers that I'm using, as you could see, the 4.99999 is almost 5. So it's like closing in on that gap right there. It says the number of people enlisting in the Army each year can be modeled by E. All right, so it's modeled by E, where E of T is the number of new recruits and T is the year since 1980. All right, so T is greater than or equal to 0, less than or equal to 20. All right, so the question is saying to us now, what does E of 7 really represent? Now, E of 7 simply represent the number. It's going to be, this represent the number of new recruits. It represents the number of new recruits in 1980 plus 7, that's 1987. All right. So in 1987, because this 7 will be added to 80, because remember, it was since 1980. So we're adding 7 to that, and that is how we're getting our 1987. So we have to take in context of what year are we running from. All right. All right. So we have that. So let's take a look at the B part of the question. So the B part of the question says, guess what? What does E of 7 minus E of 2 all over 7 minus 2 represent? The moment we're seeing this huge gap from 7 to 2, this is going to be, it's dealing with the average. This is the average rate of change. Definitely, it's the average rate of change in number or in the number, in numbers of new recruits per year from, and then we're going from 7, so from 2 years to this, it's from 1982 up to 7 years from 1980, which is 1987. What does E of 7 minus E of 6.999 all over 7 minus 6.999 represent? Basically, that is going to be the instant. It's going to be, well, it's an estimate, basically. All right, let us put it like this. It's an estimate, or we could say a close estimate. All right, so yeah, it's a close estimate to the rate of change of new recruits per year in that particular year. So in 1987, because it's close to this, we're closing in on that year right there. So that's what it really represents right there. Let's close this off with the final question. So the final question says the number of jobs created in US for the 2021 economic can be modeled by J, where J of T is the number of new jobs and T is the month. Okay, so T is in the month. For T is represented to the month. For T is greater than 0 and less than 12. All right, so this is like a 1 year. We're moving from January to December. What does J of 3 represent? All right, J of 3 is going to represent the, it's going to be the number, of new jobs. So it's the number of new jobs in March. And why March? Because March is the third month here, because we're dealing with it like that. All right, B, what does J of 6 minus J of 2 represent? Well, the moment we're seeing this huge difference between the numbers, it's going to be an average rate of change, right? So it's going to be an average rate of change within context of the question. So this refers to the average rate of change in number of new jobs. So new jobs created per month from, so this would have been the second month, which is from February to the 6th month, I'll say June, right? From February to June. All right. Now, what does J of 10 minus J of 9.999 all over 10 minus 9.9? So it's the same thing. It's a close estimate. So it's an estimate, yeah, but it's very close. So it's a close estimate to that particular rate. So to the rate of change of new jobs created in the 10th month, October. Here we go. Of which the year 2021, right? So basically that's it. See you next time.